We'll talk about what are combinations, how are they different than permutations, and how we can use them in probability. Before we get there, let's talk again about what we already come so far. We talked about multiplication counting principle, also known as the fundamental counting principle, and we've talked about permutations. And so understanding this is really key to understanding combinations. So just as a brief review, last time we learned how to count the number of arrangements where order matters. Again, that's kind of a hard phrase to understand, but what it means is if you have A, B, C, that would count as a different thing than ACB, which would be different than BAC, which would be different than BCA, CAB, CB. These are all different things. If you want to count these all as different things, that's a permutation. Order matters. So if it's like first, second, third, or I don't know, king, queen, jack, I don't know, best, second best, third best, and where the order matters, that's a permutation. Again, the formula for permutation is NPR, where you put the n, the number you're pulling from here, and the number, the total that you're pulling from is n, and r is the number you're selecting, where order matters. It's n factorial over n minus r factorial. So just as a reminder, let's say I've got 5 students, A, B, C, D, and E. Abe, Brianna, Carly, David, and Emma. They're all trying out for goalie, and the coach is going to select one person for the goalie randomly and one person for the backup randomly. How many different possibilities are there? So because this is such a small problem, from 5, we're picking 2, we can actually count the possibilities, right? You can have Abe, Brianna, Abe, Carly, Abe, David, Abe, Emma, Brianna, Abe, Brianna, Carly, Brianna, David, Brianna, Emma, Carly, Abe, Carly, Brianna, Carly, David, Carly, Emma, David, Abe, David, Brianna, etc., etc., etc. We could actually just count that, but we're not going to do this, the sample space, because again, when these numbers get bigger, it gets insanely large. So first that question we ask ourselves, does order matter? So you could just try it in your head, okay, if Abe is the goalie and Brianna is the backup, is that a different situation than the Brianna is the goalie and Abe is the backup? Is AB different than BA? If so, yes, we use permutations. If no, we use combinations. Okay? So in this case, it is yes. So we could use the permutations formula. Or again, anytime you have permutations, you can use the multiplication counting principle, also known as the fundamental counting principle. And so for that, we would just consider, how many different possibilities are there for the starting and how many are there for the backup. Okay, so again, here the order matters, so we're going to use permutations. We're selecting 2 people from 5. And so first off, for the fundamental counting principle, I have 5 possibilities for my starting goalie. I have these 5. And then once I select one of them, I only have 4 left for the backup. So 5 times 4, there's 20 possible. If I want to go to my permutations formula, again, it's 5p2. From 5, I'm selecting 2 where order matters. 5 factorial in the numerator over 5 minus 2 factorial, 3 factorial in the denominator. 5 times 4 times 3 factorial over 3 factorial, we're left with 20. Again, these are the same. Or you can count the sample space. Again, we saw the sample space is 20. 20 people. There we go. All right, now let's talk about how is combinations different. And so illustrate, let's have a very similar situation. But let's say the principal is considering the same 5 students, A, Brianna, Carly, David, Emma, A, B, C, D, E. From these 5, I'm going to select 2 students for a 2-person committee. How many different 2-person committees are there to select from 5? And so again, here we think, does order matter? Is a committee of Abe, Brianna different than a committee of Brianna, Abe? And so since they didn't make any distinction like, oh, you're the president and you're the vice president, no, there's just a committee. So AB is the same as BA. And so I don't actually want to calculate these. I don't want to actually use permutations. Order, they shouldn't be counted separately. They should be counted as one thing. And so to see where we get our formula for combinations, first, let's pretend like it actually does matter. Let's pretend like it is permutations. And so to remind ourselves, right? So again, combinations is when order doesn't matter. A, B is the same as BA. If order did matter, again, the answer was 20. There was 20 different possibilities. 5 times 4, right? 5 for the first slot, 4 for the second slot. But instead, let's think about this. We don't want to count all of these because, again, Abe Brianna is the same as Brianna Abe. Abe Carly is the same as Carly Abe. Abe Emma is the same as Emma Abe. So what we want to do is we want to only count half of these. Each one of these, this matches up to this. I want to count this as one thing. I want to count this as one thing. AD, I want to count the same as DA. And so basically, I want to divide by the factor that I'm overcounting. So if we think about it, the factor that I'm overcounting by is 2. Instead of 20, I want AB to count as BA. And we can figure out this factor by thinking about, okay, since I'm selecting 2, I've got 2 possible for the first one times 1 possible for the second one. So you can think of my overcount factor as a factor of 2. So instead of 20 possibilities, I have only 10. So that's confusing. Don't worry. The key point is to realize that for combinations, order doesn't matter. AB counts the same as BA. We're going to use almost the same form as permutations, but we're going to divide by this extra number here that really counts as the amount that we're overcounting by. Okay, so I'll introduce the formula just after one more example trying to illustrate this. Okay, so again, let's say I've got 4 pizza toppings that I'm going to vote on for best, second best, and third most popular in California. So I've got pepperoni, onion, sausage, and tomato. I want to count the total possible ways that these could be ordered. So from 4, I'm selecting 3. So let's think about this situation. Does order matter? Is pepperoni being the first, onion being the second, tomato being the third? Is that different than tomato being first, onion being second, pepperoni being third? If yes, that means order matters. If no, order doesn't matter, we use combinations, right? Yeah, order matters permutations, order doesn't combinations. All right, so again, if you look at this, the answer is yes, right? Pepperoni, onion, tomato is different than tomato, onion, pepperoni. So we're going to use permutations. So that means order matters. We can use the fundamental counting principle or the permutations formula. Again, the multiplication counting principle, we could say, okay, since I'm selecting 3, best, second best, third best, I've got 4 possibilities for the first one. I've got 3 for the second and 2 for the third. 4 times 3 times 2 is 24 different. And again, you can look at the sample space. Here they are, POS, POT, PSO, PST, all the way down here. Again, these are all the different ways I could select 3 for the best, second best, third best out of 4. And the permutation formula also works, NPR. So from 4, I'm selecting 3 where order matters. 4 factorial over 4 minus 3 factorial gives me 4 times 3 times 2 times 1, which is 24. So all of these ways would give us 24. Okay? Now let's consider a similar idea, except let's say I've got a coupon for a free 3-topping pizza. This pizza place only has 4 toppings left: pepperoni, onion, sausage, tomato, just like the previous problem. How many different pizza possibilities are there? So for this question, let's think about, does order matter? Is a pizza pepperoni, onion, sausage different than a pizza of sausage, onion, pepperoni? Right? In this case, we see the answer is no. Right? So that means we're going to use combinations, right? Pepperoni, onion, sausage is the same pizza as sausage, onions, pepperoni, which is the same pizza as onion, sausage, pepperoni, which is the same as onion, pepperoni, sausage, etc. So what we want to do is, again, combination is almost the same formula, but I want to count all of these as the same thing. You know, pepperoni and sausage, onion, sausage, pepperoni, all of these should really just count as one pizza. And so first, again, let's pretend if order did matter, again, from the previous problem, the number of possibilities is 4 times 3 times 2, or 24 different pizzas. But I'm overcounting. By what factor? Again, this is because we have combinations, order doesn't matter. What we think about is, well, since how many different ways are there what is my overcount factor? Well, since I'm selecting 3 toppings, I've got 3 possibilities for this one, 2 possibilities for the second one, and 1 for the third. And so that's 6. You can also write that as 3 factorial. So my actual number of pizzas is not 24, it's 24 divided by 6, because again, I'm counting all these as 1. I have only 4 pizzas possible, right? So pepperoni, onion, sausage, because all of these 6 just kind of meld into this. Oops. Pepperoni and tomato, onion, tomato, sausage, and tomato, sausage, pepperoni. So the total number of pizzas is only 3. Okay, so again, don't fully have to understand, just realize that the combinations are very similar, except we have this extra overcount factor that we're dividing by. And so here's the formula for combinations. So formally, a combination is a selection of R objects from a group of N objects where the order does not matter. So again, if that phrase is confusing to you, think about it like, is ABC the same as BCA? Right? If I don't want to count, if I don't want to count them separately, that's combinations. If I should count each of them as different things, each arrangement is different, that'd be a permutation. Right? So again, in other words, you count ABC, ACB, BAC, BCA, CAB, and CBA all as the same thing. Order doesn't matter, these all count as one thing, that's a combination. If you want them to count as separate things, that's a permutation. And if you notice the formula, it's n factorial over n minus r factorial over r factorial. It's almost the same thing except for this extra r factorial. What is that? Again, that is just the overcount factor. it's this idea that instead of counting all these as 24, I'm going to divide by 3 factorial, which in this case was 6. We divide 24 by 6. Our real answer was only 4 because I'm counting all of these things, 6 pizzas, as 1 pizza. Okay? So let's practice a few where we have to figure out is a permutation combination, and then let's just use the formula. All right, so let's say I'm buying. This doesn't actually look like the In-N-Out menu, but it's close enough. It kind of looks like it, so let's pretend. So let's say you're going to buy 2 drinks at In-N-Out. Let's say there's 12 different drinks. Again, I think there's actually a little bit less than that, but whatever. How many different ways can you purchase 2 drinks? Okay, so again, I've got 12 possibilities. These 6 sodas, 2 of these things, 3 shakes, and 1 water. So total of 12. I'm going to pick 2. Does order matter? Is Coke Sprite different than Sprite Coke? Right? No. Right? It's the same thing. Order does not matter, so I'm going to go combination. Okay, so because that, if I'm just counting how many different ways are there to do that, so I'm going to pick from 12. Again, this is the total pool I'm pulling from. 12C2. So I'm going to pick 2 from 12, order doesn't matter. Again, formula-wise, it's 12 factorial over 12 minus 2 factorial. Again, this part is the same as the permutations formula. The only difference is I add this extra 2 factorial. Again, what is that? That is the overcount factor. I don't want to count Coke Sprite as the same as Sprite Coke, so I'm actually going to shrink my number. So if you want to actually do it without a calculator, you can write it out. 12, 11, 10, 9, 8, 7, 6. Notice that the 10 factorials cancel out, so I'm left with 12 times 11 over 2 times 1. So you can also cancel out 12 times 2 and get 66 ways. Again, another thing you can do is just go to Desmo and just type in NCR, instead of NPR, parenthesis, 12, 2. So it's just saying, if you're picking 2 things from 12, where order doesn't matter, there's 66 different ways to do that. 66. If you actually want to look at the sample space, here's what it looked like. Coke, Diet Coke, Coke Root Beer, etc. Again, notice that there's no Coke, Diet Coke, Coke here. I'm counting Coke, Diet Coke the same as Diet Coke, Coke. Okay, there's 66 different possibilities. All right, so let's say there's 27 students in this class. If I want to pick 3 of them to go help an injured student, how many different groups of 3 are there? So again, always ask yourself, is it a permutation order matters or a combination order doesn't matter? So think, is A, B, C? If I pick A, B, and C to go help the injured student, is that different than picking student C, B, A? And no, right? It's the same. So order does not matter. I'm going to count these as the same thing. So that's a combination. Okay, so maybe pause the video. How would you set this up then? Okay, so we would just say 27C3. So from a group of 27, I'm picking 3. Order does not matter. Again, the formula is 27 factorial over 27 minus 3 factorial, 24 factorial. And then you add that extra 3 factorial, which is your overcount factor. Again, you can actually write it all out. 24s cancel out. You'll have 27, 26, 25 over 3, 2, 1. You can punch that in your calculator. We get 2,925 groups. Or you can go to Desmos, type in NCR 27, 2. I'm sorry, 27, You go to Desmos, NCR, type in 27, 3, 2,925 ways. All right. Determine whether each solution involves a permutation or a combination. Then find the number of possibilities. So the winner and first, second, and third runners-up. So there's 4. Winner, and then first runner-up, second runner-up, third runner-up in a contest with 10 finalists. And selecting 2 of 8 employees to attend a business seminar. So this first one, I'm picking a winner, and then first runner-up, second runner-up, third runner-up, fourth runner-up. So 4 people total. And this one I'm selecting 2. Does order matter or not? So maybe, again, pause the video, think about that, and see if you can do it. Okay, we'll call this A, and we'll call this B. This first one, A, the answer is yes, because, again, imagine that it's like Joe, Bob, Sally, Jane. That's different if Joe is the winner and Bob is first runner-up and then Sally and then Jane. That's different than if Jane is the winner, Sally is first, then Bob, and then Joe. Those are different, so order matters. So how can I calculate that? That's a permutation. So I can say 10p4. I could do the multiplication counting principle. Also, I can say 10 times 9 times 8 times 7. Or I could do the formula, or I could punch it in Desmos, but I would get 5,040 possible ways. And we're just counting the number of possible ways. This is not probability yet. On the other hand, for this one, if I'm selecting 2 from 8 to attend a business seminar, that's a combination. Because it doesn't matter whether I select Bob and then Bob Joe to go to the business seminar. That's the same as if Joe and Bob go. So order doesn't matter. So that, again, would be a combination. That's 8C2, 8 factorial in the numerator, over 8 minus 2 factorial, which is 6 factorial. And then for combinations, we have the extra overcount factor, 2 factorial. And again, you can punch it in, or you can do the math. 8, 7, 6. The 6's become 1 here. We get 8 times 7, 56 over 2 factorial, or 28. Or just punch it into Desmos. A few more. Now, probability. You have to calculate 2 things. You have to calculate the number of ways to be successful on the top, and then you have to count the total number of ways on the bottom in the denominator, right? That's probability. It's the number of ways to experience success, successful outcomes over the total number of outcomes. So let's say the yearbook, there's 14 photos, and they're going to pick 2 of them. What's the probability you and your friend end up at the top? Now, this is a little bit ambiguous about whether order matters, but I'm just going to assume that order doesn't matter. So first we think, what is the denominator? What is the total number of outcomes? I've got 14 pictures. How many ways are they going to pick 2 from 14? Again, it's a little bit unclear here, but they mean order doesn't matter. So like you, your friend is the same arrangement as like your friend, you. I count this as this one thing. So on the bottom, it's 14C2, which again, we use the formula, is 91. There's 91 different ways for those photos to be arranged. On the top is how many ways is there to be success? And in this case, success is me and then my friend are both there. So again, it's order doesn't matter. From 2, I'm picking 2. 2, I'm picking 2. Now again, 2 minus 2 gives me 0 factorial. 0 factorial is defined as 1. And so we're just left totally with 1. So it's 1 out of 91. One way to be successful out of a total of 91. A few more, or a couple more. You draw 5 cards from a standard deck of 52. You win if the hand is 3 clubs and 2 diamonds. What's your chance of winning? Okay, it's a tricky problem, so just kind of watch and maybe you can do the last one. Now, think about cards. If you have in your hand ace, king, queen, jack, is that different than jack, king, queen, ace? It's not. So we're not going to use permutations. We're going to use combinations, right? The order of the hand doesn't matter. Only the cards in the hand matter. So first, what's the total number of ways to draw 5 cards from 52 total? Again, if order doesn't matter, that's our denominator. So the total number of 5 card hands possible, there's so many different 5 card hands possible, that's 52C5. 52C5, that's my denominator. That's the total number of ways to draw 5 cards from 2. Now, what goes on top in the numerator? I want to get 3 clubs and 2 diamonds. So by the multiplication counting principle, fundamental counting principle, we can multiply the number of ways to select 3 clubs, and the number of ways to select 2 diamonds, and that'll be the total number of ways to be successful, right? Because I've got this many ways to get 3 clubs, and then for each of those, I can have any of those ways to get 2 diamonds. So the ways to get 3 clubs it's 13, because there's 13 different diamonds. From those, I want to grab 3. Times from how many ways? 13 clubs. I'm sorry. There's 13 clubs. I want to grab 3 of them. Times, for each of those ways, I can also grab from 13 diamonds 2. Right, I'm grabbing 2 of them. And so just if I want to put those as numbers, there's 286 ways, right? 13C3. Again, you can punch that into Desmos, NCR 13, 3. There's 286 ways to grab 3 clubs, right? You have the 2 of clubs, the 3 of clubs, and the 4 of clubs, 2 of clubs, 3 of clubs, 10 of clubs, 2 of clubs, 3 of clubs, jack. There's 286 of those. Again, order doesn't matter, so you're not counting 2, 3, 4 the same as 4, 3, 2. They're just all as one thing. And for each of those, there's 78, right? There's 13C2, 78 ways to grab 2 diamonds from these 13. So total 286 times 78 gives you 22,308. The problem is that that means there's 22,308 ways to be successful. The problem is there's 259,000 possible. Sorry, 202 million. Sorry, let me just push down here. NCR 52.5. There's 2,598,960 different hands possible. So if you're playing a card game where you're picking 5 cards, there's 2.5, almost 2.6 million possible hands. Okay? So out of those 2.6 million, only 22,000 are going to give me 3 clubs and 2 diamonds, which is a very low percentage, less than 1%, 0.86%. Now, something that confused me was that why can't we, this confused me earlier when I was learning this, why can't we do this? 13 out of 52, so this would get you their first clubs, times 12 out of 51, your second clubs, times 11 out of 50, your third club, times, and then since I want diamonds next, 13 out of 49, because there's 13 diamonds left out of 49 cards, times 12 out of 48, right? There's 48 cards left, there's 12 left. And that would give you a number that's smaller. Why doesn't that work? And the reason that doesn't work is because that's giving the specific order club, 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 D, D. We've already established that order doesn't matter. And so you would have to calculate all the different ways, diamond, diamond, club, 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 diamond, club, club. And so that's why this is not going to do it. You're better off using combinations instead. Right? You're better off saying 13C3 times 13C2 over 52C5. Okay, now I know that's tricky, so let's try one more, just as another example. So this time, you're not selecting 5, you're selecting 4 cards from a 52 card deck. What's your chance of getting 3 spades and 1 heart? So again, calculate the number of total 4 card hands possible, and what's the number of ways to get 3 spades? By the multiplication counter principle, you can multiply that by the number of ways to get 1 heart, and see if you can calculate the probability. So maybe pause the video and try that. All right, so here it is. So again, your total number of 4 card hands possible is 52C4. We can punch that in, 52C4. That's 270,725. There's 270,725 possible 4 card hands. Out of those, in the numerator, how many give me success? So how many ways are there to get 3 spades out of 13 times how many ways to get 1 heart? So 13C3 times 13C1, you can punch that in. 286 times 13. So for each of these 286 ways to get 3 spades, you have 13 different possibilities to get 1 heart. 2 of hearts, 3 of hearts, 4 of hearts, 5 of hearts, 6. 13 different possibilities for each of these 286, which means total you have 3,718. Right? You punch that into decimals as well, right? 286 times 13, 3,718 ways to be successful out of a total, though, of 270,000. So again, we have a small chance, about a 1.37 chance of being successful. Okay, so in summary, combinations are similar permutations, except order does not matter. Try the homework. I'll post a hint later on.